So good morning, everyone. Actually, it's 12:30, but haven't been out of the house because of the snow on Monday. In any case, I've been asked some questions about correlations and straightening of a scatter plot. So to be clear, a scatter plot is a graph made up solely of points. So I've got two variables. Suppose maybe I've put height on the x-axis and weight on the y-axis, because I'm hypothesizing, I'm suggesting that maybe a taller person will be heavier. That is, I think that if I measure different people, the height will have some explanatory power on the weight. So I've put the height as the explanatory variable and the y as the response, and the weight as the response variable. Okay, x is always the explanation, y is always the response. So if I think that one depends on the other, that's how I'm going to set it up. Okay, so I've constructed a scatter plot. Correlation is the degree to which that scatter plot is linear. And it can be between -1 and 1. In the middle, at 0, if the correlation were 0, then I would say this data is not linear. It doesn't mean there is no relationship between the x and y. It just means the relationship is not linear. On the other hand, if it were 1, there would be a perfectly linear graph of some slope. And if it were -1, there would also be a perfectly linear graph of some slope, except the slope would be negative. So as height increases, weight would be decreasing, whereas with +1, as height increases, weight would also be increasing. And at 0, I've just got a scattering of plots, of points. That is to say, if the correlation is 0, knowing the height gives you no ability whatsoever to make a reasonable prediction about the weight. Whereas when it's 1, it lets you figure out exactly what the weight will be. And so too, if it's -1, you can follow that line and figure out exactly what the weight will be. Okay, now, when we look at linear regression, what we're actually looking at is how to calculate that correlation and how to use it to construct the line. That is to say, if the correlation is 1, obviously I'm looking at points that are in a line, and I can easily pass a line through them and figure out its equation. If it's 0, the best line through that is going to be some horizontal line. But when the correlation is between 0 and 1, or between 0 and -1, I can construct the best fit line, a line that goes through the points and stays as close as it can to all of them. And your book describes that as the least squares, because what it does is it minimizes the square of the distance of each point from the line. And so in linear regression, which I wasn't asked any questions about, but I want to mention it, we're calculating that line, and to do that we have to calculate the correlation exactly, to know exactly what the correlation, which is called R, is. And so to calculate that, I'll just quickly say that it relies on what we did last week, the standard deviation, to give a common unit. So when I'm actually trying to calculate directly what the correlation is, which I won't be asking you to do, I'll be asking you to use your calculators on data sets. But to understand the principles, you need to understand when I want to calculate precisely what the correlation is, what I'm actually doing is not comparing the variable on x to the variable on y, but rather the z-score of the variable on x to the z-score of the variable on y. And there's a lot of mathematical results from that, which I will discuss in class this week. But the most important is that if I find the mean on x, that is to say it has the point that has a z-score of 0, and the point that has a y z-score of 0, that point will be on the graph. So that graph will always pass through the origin. And the highest its slope can be is 1. I will show why in class because that requires a bit of a proof and explanation. But the slope of the line formed by taking the standard deviations is exactly what the correlation is. Okay. So the correlation is just that slope. We'll see that in class. I just wanted to mention that quickly for now. Now, on the straightening, suppose I got a pattern of points that shows me there is clearly a relationship, but it's not linear. Okay. I don't have techniques to put the best parabola through it or the best exponential curve. But what I can do is, just like I did earlier when we were talking about histograms and data distributions, is I can apply a transformation. I can apply a power or a root or a logarithm or something like that to one or both of the variables and hopefully eventually get a linear graph. If the best fit curve through those points were in fact a parabola, then by taking the square root of the y's, you should get a linear curve. Okay. Or by squaring the x's. And there's a few other things we can try. But the idea is, I'm going to develop a point where, the best fit line where a parabola, I would best do it by squaring the y. In any case, again, I'm not going to expect you to know that. I'm not going to expect you to do that. I'm going to expect you to understand the principle behind it, which is to say, I am modifying the data and getting a new graph. Instead of having height on the x-axis and weight on the y-axis, I might have height on the x-axis and the square root of weight on the y-axis. So if a person is 5'2" and 200 pounds, the corresponding point is no longer 5'2" on the x-axis and 200 pounds on the y-axis, but 5'2" on the x-axis and the square root of 200 on the y-axis. I'm going to apply these different transformations, and there's an empirical rule in your book that shows you a technique to find the best approximation by experimentation. Until I find the best approximation, then I can apply the techniques of the linear regression to it. So when two variables have a relationship but it's not linear, we say that they are associated but not correlated. Correlated means it's a linear relationship, not just any relationship. Okay. Now you might know this, and I even said it, that the discussion here of reexpression is exactly the same as the discussion of reexpression back when we talked about histograms. And I'll explain this more in class, but I want to touch briefly on why that should be. Your textbook just mentions it, it says it's amazing, and moves on. I want to give you a little bit more explanation as to why that should be, and why it makes some sense. Now, thinking about it, I mentioned before that when I form the linear regression, I calculate the correlation by comparing the z-scores of each height, for example, with the z-scores of each weight. And I know that that maps means to means, which is called regression to the mean. And we'll go into what that predicts in various probability situations, such as flipping a coin or rolling a die, things like that, on Wednesday. Just note, though, I'm comparing z-score to z-score. Z-scores are the most valuable and predictive when the data is symmetric. Reexpression in that chapter was designed to make the data more symmetric. So here what reexpression is actually doing is making both values more symmetric. The more symmetric the frequency of the x values is, and the more symmetric the frequency of the y values is, the closer the correlation will be. So the reexpression is actually doing the same thing. It's making standard deviations work better for each. And the more descriptive the standard deviation is for both variables, the stronger the linear relationship will be. But this will require a bit more in-depth discussion, which we will do on Wednesday to see why all those things hold. I'll go through a couple of examples with you in class to illustrate how all those things interrelate. All right, well, thanks for your questions, and please write if you have any more. Thanks.